Professor, you are so funny, ha ha ha.
Hi, Dixie. Yeah, Daddy love you, but I gotta work now. Hey, kids, get the dog. Oh, hi. I'm Professor Walter Brainstein, and this is Physics 101. If you want Physics 102, that's it down the hall. This is Physics 101, the easy stuff. It's called Perihelion Engineering. The universe in a nutshell. Physics 101. Planet, moon, orbit, closest point called perihelion. I'm professor of Scientology. I'm not doctor, doctor for sick people. I'm for crazy people. Physicists are crazy people. We say all kinds of stuff. Nobody knows if it's the truth or not. Well, we gotta prove it with mathematics. Sometimes it's good and sometimes it's not. We're going to talk about differentials. Hard, soft, light, dark, cold, hot. Did I do that before? Did I do that before? Did I do that? Did I do that? Did I do that before? Hard, soft, light, dark, cold and hot. Yeah. Lucy, show the picture.
Okay, Professor. Physical differentials. Hot, cold, light, dark, hard, soft. Physical differentials can all be related to the same thing, motion, or rather the energy of matter. Hot is active particles, cold is less active particles, light is active particles and dark is less active particles, and hard is high density active particles and soft is low density less active particles. In physics it is described as entropy versus isotropy, and I wish to bring to the understanding that zero does not exist.
Isn't she wonderful? Lucy's so smart. The thing about zero, that's always been a problem. In calculus, they got to have a limit 1 to 0. Problem is, zero doesn't exist. And that's the thing here on the XY graph. Because of mathematics, we got to have a 0, right? Okay, because of crossover and plus and minus and goes this way and it goes that way and that's 0. But see, the universe don't know about 0 because it gets smaller and smaller and smaller and it gets bigger and bigger and bigger and it don't have a 0. You see, that's the problem. It got infinity. And you can't use that in an equation because it makes everything not work, You got to have a 0. Or do you? How do you live without 0? The problem is, 0 would have to be absolutely nothing. And that's the problem with the Big Bang. Because they get closer and they get closer and they get closer to the 0, but they can't figure out what's before the 0. So they got to have something, so they say, well, it was all infinitely small, So that's the problem. When physicists want to tell you that it's infinite, anytime they use the word infinite, they're crazy. Because infinite is impossible, but yet the universe did it. And I'm going to prove that to you. The universe is infinite. Like Einstein wanted to originally say, the universe was infinite. Okay, Lucy got some more for you.
For zero to exist, that would mean no motion or particle activity over infinite time. It would also mean that a particle must have zero radius as proposed in some theories. And when you hear the terms absolute zero as in 0 degrees Kelvin, they are in error. Absolute zero would mean no molecular or atomic motion over infinite time. Remember this principle.
Oh, hi. I just turned on the radio and did just some music. Lucy's so smart. She says everything so much better than me. That's why I let her do it, because she reads so good, and I don't read so good, I'm kind of slow. So we're going to make a simple observation, this is important to the thesis. And what it is that a simple observation is that when you compress a gas, it gets hot, and when you expand a gas, it gets cold. Okay, it's real simple. Like you go out, you got a flat tire on your bicycle, and you get out the bicycle pump, and you start pumping, and you notice that the pump gets hot. That's because you're taking molecules that are real busy up here, and you're compressing them down into a small space, and they bounce around, and they have to give up their energy to give it up to the pump. The pump gets hot, and the tire gets bigger and bigger and bigger. Then what happens when you let the air out of the tire? It gets cold. That's an interesting thing. This is going to be what we're going to talk about in thermodynamics. Lucy, take it away.
Thanks, Professor. First law of thermodynamics. Energy can neither be created nor destroyed, it can only change form. Second law of thermodynamics. Energy is entropic in nature. Translated, energy radiates outwardly and cannot be reclaimed. It is forever outwardly expanding.
Thank you, Lucy. Now we're going to talk about another simple observation. It takes fire to make fire. See the flame, see the flame. It takes fire to make the fire. The fire started in my muscles. The muscles pick up a lighter. The lighter go over and go, and the thing spark, and it turned to gas, and it turned on the flame on the alcohol burner. You know, it took me to take that, to do that, to do that. It's called causality. It always takes something to make something else happen. It takes fire to make fire. Put out the fire.
Another simple observation. It takes fire to make fire. In order to make particles collide, it takes other particles to make them collide. Rub your hands together and they get warm, but it was the muscles in your arm which were metabolizing oxygen and carbon. When the muscles contract, that produces carbon dioxide or CO2 that you exhale in your breath. This made your muscles move to rub your hands together. More scientifically, oxygen was collided into carbon and the collision created carbon dioxide and released the energy to move the muscle cells. Simply, it takes an action to cause another action. Energy is not realized until particles collide and form new compounds.
Lucy's going to tell you something really important now.
What is a particle? Any globule is a particle. Since the ultimately small particle cannot be defined because zero does not exist, then any mass of any size is considered a particle. A moon is a particle made up of other smaller particles. Likewise, an atom is made up of protons and neutrons and electrons. This definition of an atom will do for now. Particle collision. This represents all particles including moons, planets, stars, galaxies, as well as molecules and atoms and the quantums of quantum theories. Trajectory and position and time come down to the Heisenberg uncertainty principle.
Isn't she wonderful? It's called the Heisenberg principle.
That is called the Heisenberg uncertainty principle, Professor.
Okay, physicists, they know it's particles bouncing around and they want to see those particles. So they look smaller and smaller, and they get a microscope, they look down, and that ain't small enough, so they get an electron microscope and they look down smaller and smaller and smaller. And what they realized, this man Heisenberg, was that what you're looking at it with is the photons, and the photons are moving the electrons, so you can't really see it without it moving. So as soon as you try to view it with photons, the photons move the electrons, so you're not really seeing the position of the electron because the photon's moving it. You know, this is an important principle about particles moving particles. Now Lucy's going to show you some particles, really neat pictures.
Thanks, Professor. With our extensive consideration of particle collision from the large to the small, here is what can be known. All possible trajectories in 3 dimensions can be calculated, as well as mass and velocity. The only unknown, because a frame of reference cannot be determined, is rotation. Here are 2 particles traveling in space with velocity, direction, mass, and a time of collision that is calculable. If you cannot see this on a quantum scale, then think of it on a terrestrial scale, such as moons and planets and asteroids, which we see collide all the time.
Thank you, Lucy. So what we learned was that we can figure everything about a particle motion through space. You know, go here and go there and go there, but the only thing we can't figure out is the rotation. You know, because it don't matter if the collision come together, okay, if there's any rotation, that's 1 arc second in infinity, it's going to skew. It's going to go crooked. And it's impossible to know the rotation. So the particles come together, they go like this, right minute, they go whoop, and they twist it. So, and that's because zero doesn't exist. It would have to be zero rotation over infinite time, or every collision is skewed. And you look at the universe, it's all skewed.
The only indeterminate The only thing that cannot be calculated is the rotation of the particles in 360 degrees spherical. This is incalculable over infinite time. That is, if either particle has any rotation of even 1 arcsecond over infinite time, the collision will skew into anything other than a perfect symmetrical shape and direction. Since zero is impossible, zero rotation is impossible. For zero rotation to exist, this would mean that there is not 1 arcsecond of rotation over infinite time. As a result, all collisions skew. The substructure of particles large or small reduces to isotropic equilibrium that evolves over time in the confines of the first and second laws of thermodynamics and results in all matter being round or evolving to be round and made of smaller particles. All particles, no matter how small, are made of smaller particles. Antimatter is someone's dream. Dark matter will be found to be a 1.0 to infinity squared, the only true use of the term infinity.
But I did like the part where she said antimatter is somebody's dream. You know, that's in Star Trek. There is no antimatter. They think on the other side of the Big Bang, maybe that's a antimatter, and they keep trying to make the antimatter. But let me clue you in, buddies. There ain't no antimatter. It's all real matter. And then she said, dark matter will be found to be 1 to the 0 infinity squared, which is the first real use of infinity, is in dark matter. Dark matter is the infinitely small. Okay, stick out your tongue and say, ah. Boy, it's dark in there. I don't see anything wrong, but what do I know? I'm not a doctor. I'm a physicist. You know? But you got halitosis, I know that. No, it's me. Take 2 minutes and call me in the morning. Okay, that Lucy, boy, she say a lot of things really fast. You know, problem with computer girls, you click the button, boy, they just start talking, and you know, before you know it, they said all kinds of stuff that you don't know what she said. Oh boy. Well, I'll tell you this. A lot of statements were made there, and a lot of them were really important. So I put on glasses so I can see through glasses. When she said subparticles, the structure of particles large and small reduces to isotropic equilibrium that evolves over time in the confines of the first and second laws of thermodynamics, and as a result, all matter being round or evolving to be round and is made of smaller particles. All particles are made of smaller particles. What happens when you get down to little tiny particles? We find out that they can't find the smallest particle because it just keeps getting smaller and smaller and smaller into infinity.
Since no ultimately small particle in all infinity can be defined, a common substructure can be assumed. Since zero is impossible, straight lines do not exist except metaphysically. Curvature is. This means, since zero is impossible, a straight line is impossible, and thus all considerations of space and time are curved, and thus also the concept of round is only a measure of isotropy or uniform measure of mass density, dependent on the resolution of the most relative smallest particle, and all real objects, globules, or masses or particles are lumpy dependent on the resolution of the apparent smallest particle of the mass.
About certain structures of the particles, like 6 around 1 makes 7, and then 3 more on top and 3 more on the bottom makes 12.
7 plus 3 and 3 is 13, Professor, and then if the center member is missing it is 12. Sorry, just trying to help.
It's like the way parts fit together from round to square. And we notice that elements, they all got crystals that do really weird things, like they go square and they go hexagon. How do they do that? And then the important thing is that all matter is lumpy. Like the Mandelbrot series, it's lumpy, and it goes in pre-patterns and does really unique things, but it's lumpy. And it's only as good as the resolution as the smallest physical particle. The smallest particle is the resolution, and then you look really close and you see that it's lumpy.
Hello, knock knock Professor, it's your turn.
Oh, you back already? Yeah, you go again with the radio. That's the Beach Boys. I'm really getting off on that. Okay, let me turn off the radio. Got Beach Boys take me back. Ooh, they didn't take me too far back. That shows how old I am. What happened when you mix red and green together? You get yuck. Now Lucy's going to talk about something really important. This is called particle collision. How everything starts out nice and uniform and goes blup, squish.
Example, here are particles made of subparticles colliding. The anomaly of the mathematical strength of the missing member. Removing the center particle calculates to an equally strong structure with less mass. This is why an architectural arch stands as strong as a solid wall. All external forces are distributed to side members and not to the center member. This structure is equally strong with less mass. This is why we see crystalline structures of elements and compounds that form other than round shapes with strengths that exceed the mass of other elements or compounds, i.e. hardened iron weighs in at 7.874 grams per cubic centimeter but is no match for carbon that weighs only 2.267 grams per cubic centimeter as graphite and 3.515 grams per cubic centimeter as diamond. The diamond is used to cut hard steel. Later electron microscope images of a diamond will show the amazing structure. Now consider particle collision. Also remember that particles can be moons, planets, meteors, asteroids, comets, even suns and galaxies, as well as molecules and atoms and atomic subparticles. Here are two molecules with a crystalline structure about to collide. In every consideration of particle collision, energy in the form of mass with velocity, kinetic energy, reorders constituents to a new equilibrium. On collision, the molecules fracture and are sent on new trajectories. If the pressure behind them is sufficient, they begin to flatten. Subparticles are thrown to new vectors. An actual particle collision is skewed in 360-degree spiral rotation. Subparticles extrude in the path of least resistance.
So we find two interesting forms in the universe. That's round and discus. Everything is round or is discus. And when things come together, they go squat, squirt. They go round to discus, round to discus. It's called hysteresis. Now Lucy's going to tell you about hysteresis. Hysteresis. Okay, I get it.
Hysteresis. Hysteresis is the natural phenomenon that occurs as energy moves through a system. Example, when particles collide, the event gradually occurs and reaches the maximum intensity of the event and then diminishes to a state of rest or post-event. Of note is the shape of the curve. Slide 16 is an oscilloscope image of a transistor switching from off to on. Capacitance causes a sine wave hysteresis that settles over time. The squiggly line is oscillations of electrons settling at their new potential energy level. A soft clay ball, when slammed to a hard floor, produces this hysteresis shape. Two clay balls collide in free space. Rotation is unknown and incalculable. Notice the hysteresis shape. Extrusion. The edge is the new event horizon as the event extrudes into new space. Energetic subparticles vectored to the edge of the collision will now have the greatest probability of colliding with the next molecule in a chain of events. Subparticles escaping under the pressure of the collision extrude perpendicularly to the direction of the mass collision. Again, rotation is incalculable. Magnification of the extruding edge. The path of least resistance. We are on the edge of a very large collision center, our galaxy. This image is from page 14, rotated 90 degrees. Notice the hysteresis form.
So now Lucy's going to tell you about probability. The most important thing. That's why everything is so confusing, because the probability that you're going to get it wrong.
probability. Make a pegboard like a Chinese pinball game. Use marbles and drop them into the game and they will fall and form the mathematical shape as shown above if the start drop point remains in the center. This is the hysteresis form that occurs throughout our existence. It occurs in space, in our physical reality and metaphysically in our conceived self-created realm. Probability over an infinite number series is a logical absurdity. What does this mean? The odds of two particles colliding in infinite space if there were only two particles is 1/infinity. Any number in an equation that is calculated against infinity is absurd because it has no meaning. Revise the equation. The odds of particles colliding if space is infinite in size and the number of particles is infinite. Infinity/infinity. That means there is an infinite probability that a collision will occur. I know, slow down and think about it.
Now, isn't that interesting what she said about probability? Okay, if you only got a few particles in space and a lot of space, you don't have a very good probability that they're going to collide. But if you have infinite particles in infinite space, there's the infinite number again. The probability of collision is pretty good. Well, and sometimes you just got to acknowledge the truth. You know, the truth is, see what's there. And stop trying to make up stuff that's not there. Antimatter, you know, it really bugs me. But it's kind of like finite minds have finite solutions. We had a beginning, so therefore the universe had a beginning. But it didn't. And when you start to realize that it didn't have a beginning, that it is infinite, then you might be able to start thinking in a different way. Don't be limited in your thinking.
We only see a small portion of the universe, and the suspicion is that dark matter causes the gravitation anomalies we see. Dark matter and dark energy make perfect sense. Particles smaller than we can detect are moving through our space at velocities and frequencies that are what we can call pre-rational. They exist and on a massive scale they collide in our real space. Infinity is difficult to think of, but it will make sense to you in time. The probability of infinite particles in infinite space becomes 1-to-1.
Here. Okay. These are some really famous guys over here. That's Albert Einstein and Max Planck. And this is Niels Bohr, the guy that invented our atom the way it is today. And that's Newton, who we probably wouldn't be here if it weren't for him. Okay, let's see. What happens when you add red to blue? Oh, it turns purple. A little more red. Yeah, getting really purple. Everybody knew that already, right? You're smart. Okay, now you gotta take notes. You gotta take notes or you're never gonna pass the quiz for Physics 101, the first episode, okay? Quiz notes, write this down. Here's number one. Number one, most important thing. All collisions are head-on. They can go this way, they can go this way, this way, but the closing velocity is the only thing that's important, and it's head-on. Lucy, show them again.
Sure, Professor. All collisions in free space can be considered perfectly head-on collisions because all lateral vectors can be removed with respect to the particle's frame of reference.
Thank you, Lucy. Quiz question number 2. Gas gets hot when compressed and cool when expanded, and the heat energy always moves outward. Lucy, show them the picture.
And I might add, Professor, this is the principle by which air conditioners work. Air conditioners are called heat pumps because they move heat.
Thank you, Lucy. Quiz question number 3. All collisions rotate because zero is impossible. Show them the picture, Lucy.
If either particle has any rotation of even 1 arcsecond over infinite time, the collision will skew into anything other than a perfect symmetrical shape and direction because zero rotation is impossible.
Thank you, Lucy. Quiz question number 4. Structures can be hollow because of the bridge effect. Take it away, Lucy.
Removing the center particle calculates to an equally strong structure with less mass. This is why an architectural arch stands as strong as a solid wall. All external forces are distributed to side members and not to the center member.
Thank you, Lucy. Quiz question number 5. Hysteresis occurs in every event. We call an event, boom, when things bump together. That's an event. Hysteresis occurs in every event. Okay, Lucy.
When particles collide, the event gradually occurs and reaches the maximum intensity of the event and then diminishes to a state of rest or post-event.
Thank you, Lucy. Okay, quiz question number 6. It's the big one. Nothing would collide if there were less than an infinite number of particles. Now, everybody in the physics community is going to argue with me and say that I'm crazy. But you want to know who's crazy? Those people that thought up the Big Bang where there was nothing. Okay? That's crazy. Okay, we'll argue this out, but take it away, Lucy.
We only see a small portion of the universe, and the suspicion is that dark matter causes the gravitation anomalies we see. Dark matter and dark energy make perfect sense.
And finally, quiz question number 7. We have a beginning and an end, but the universe did not. So if we stop thinking in finite terms, we might find out some really interesting stuff. Okay, I think this is going to conclude episode number 1 of Physics 101. It's going to get a lot of fun because the next time we're going to do some real experiments.
Finite minds create finite concepts. Professor, would you like to dance?